So now that we've looked at a lot about what strong acids do, we want to return to the idea of what exactly a weak acid is. So strong acids are characterized by a complete reaction with water. So when strong acids react with water, they fully react. We can use stoichiometry. The concentration of hydroniums in a solution is equal to the initial concentration of the acid or whatever we designed it to be. So in this case, we were looking at, say, a 0.1 molar nitric acid. So it's 0.1 molar of hydroniums actually floating around in that solution. That's how it would inform, say, the pH. And so we know that in the actual solution, it's just a bunch of nitrates, the conjugate of the nitric acid, and then hydronium ions floating around. For a weak acid, so for example, hydrofluoric is a weak acid, when you prepare a solution of that, it's a reactant-favored equilibrium, the reaction with water. So you still do make some hydroniums. The weak acid HF does make some react with water. Hydroniums are produced. There you do change the properties of water because pure water has 10 to the negative 7 hydronium. So you have to make a weak acid doesn't have to make a ton in order to cause a change. And so the concentration of hydroniums at equilibrium is not equal to the initial concentration. So this 0.1 molar HF that you started with, you're not going to lead to 0.1 molar hydroniums in a weak acid solution. But for what is a weak acid, any molecule that can donate H+, that's not on our list of strong acids, is a weak acid. So we had 6 strong acids. Everything else, it's got to be weak. So that's why we just list out all the strong acids, and by omission, if something's not on that list, we can assume a weak acid. So HF isn't listed on that list, it's a weak acid. So if we zoom into the molecular level of, say, HF, so this would be, say, our HF molecules, when they're dissolved in water, because it's a weak acid, most of the molecules don't donate. Most of the molecules stay as the reactant in that reaction with water. Similarly, it's all water molecules. There is going to be some hydroniums that are created. It's not that there's no hydroniums that are created, just most of the acid molecules don't react and don't lead to the creation of hydroniums. That's what the weak corresponds to. That you don't have a high change or a large change in pH because you don't have those. You're not strongly creating a bunch of hydroniums. Weak bases are the same idea. Weak bases react incompletely with water, so you cannot use stoichiometry to determine how many hydroxides are created. And again, weak bases are kind of just any molecule that can accept an H+ that is not a soluble hydroxide is a weak base. So all of the nitrogen bases are all weak bases. It was just that group 1A and 2A, when those metals are paired with hydroxides, that's where your strong bases are. Everything else is a weak base. So all the other hydroxides, so like iron hydroxides, are going to be weak. And then, nitrogen bases and sort of anion that can accept an H+ is going to be a weak base. Got to use equilibrium. I want to talk about some of the context and connotations of this idea of weak versus strong. And really all it is looking at is how effective that acid is at causing changes in pH. So for example, if you have, say, 0.1 molar HNO3 and 0.1 molar HF, you would expect that the pH of the nitric acid solution will be lower because it is at a lower pH. Because it's a stronger acid, it's going to push the pH lower because that's what makes the strong acid is. As long as that pH concentration stay the same, you go to a lower concentration, the pH will always be lower for the strong acid solution. But you can cook things up if you have say a low concentration of a strong acid and a very high concentration of a weak acid, that you could get a lower pH. Okay, so just because it's a weak acid does not mean it is safe or that it isn't an acid or that it's a bad acid. HNO3 at a low concentration is much safer than HF at a high concentration. It's also important to note that strong versus weak only describes the reaction with water. Hydrofluoric acid dissolves your bones. It also dissolves glass. So like working with it in a lab is difficult because you can't use glass beakers because it'll dissolve the beaker and then just pour out onto the surface. So HF, even though it's a weak acid, is some gnarly stuff that we do want to be mindful of, is potentially very dangerous. Similarly, we use bases are really common cleaning supplies. So for example, like oven cleaner, like Easy Off or drain cleaner, there's just like a lot of sodium hydroxide in there, potassium hydroxide. And one of the ways that they work to, I think when we previously talked about this, that they introduce oxygens. What they really do is they remove a bunch of H pluses. Say you have grease, all of a sudden these strong bases come in and start ripping off H pluses. Then you have a bunch of O minus left over. And if you think that O minus, all of a sudden that's really polar, the molecule, and it's going to dissolve. If you use, say, like less harsh chemicals, it's things like weak acids and weak bases like vinegar and baking soda, because those are less, they're just not as sort of efficient at reacting. They're not as aggressive at reacting, but they're still trying to do the same thing. It's still acid and base chemistry that you're using here. And one of the things about that is you have to use a lot of vinegar and a lot of baking soda in order to accomplish that reaction. We can also kind of look back on, say this case, we talked about the fact that when you're, say, these like drinks or whatever that have these pHs, you're using a lot of electrolytes to shift the taste. And you'll note you're using a weak base. So you can put a lot of this base in there. Carbonate is a weak base. You can put a lot of that in there and it only pushes the pH a small amount. The pH in this case is like 9.5. You wouldn't want to drink something that has like strong base in it, because if it was like a pH 12, because it would really move the pH a lot. And so what this means, you can put a lot of weak base into this solution, carbonate here in this case, and it's going to change the taste a lot, and it will move the pH a little bit and affect some of the properties like that, but it doesn't really make it a dangerous thing, and it doesn't make it like a super basic solution or anything like that. One other thing we want to consider is that weak versus strong designations are only talking about the reactions of those molecules with water. So when you start to go back to the idea of acids and bases reacting with each other, so acetic acid, here this is the active ingredient in vinegar, that's a weak acid. Ammonia is the active ingredient in Windex, that's a weak base. The equilibrium constant for this reaction is 10 to the fourth, so 31,000. That's not crazy huge, but that's much bigger than 1. And this reaction really does go to completion. And in general, weak acids and bases still react completely with each other. So yes, they don't do a very good job of reacting with water because they're weak, but they react very strongly with each other. And strong acids react very completely with all weak bases, and vice versa, strong bases with weak acids. So the strong weak designation only applies to the reaction with water. If there are other, say, molecules present, there will be a very strong reaction with those. So for example, when we were looking at, say, reacting drugs with an acid, we use a strong acid with that, and that will lead to a complete and total reaction. We know that this molecule can be a base because of the nitrogen. It's a weak base. It's a pretty weak base. So we react it with a strong acid, and it still will react all the way to completion. So this straight arrow is showing stoichiometry, and you get a full reaction of that weak acid, or weak base, sorry, fully all the way into that product, which is what you want to create. And so just because it's weak that just means it doesn't react completely with water. If you react it with a strong acid, it'll go the whole way. And conversely, when you're choosing an acid to do for this, we don't use acetic acid in pharmaceutical drug manufacturing because we want to be sure it's really pushing that reaction all the way to completion. So just throw the sledgehammer that is a strong acid. This efficiency of strong acids is why we use them throughout experimental chemistry. If we look here, say you wanted to get a solution as to a pH of 1. You need 0.1 molar HNO3. You need 10 molar HF. That is 100 times the concentration. And if your only goal is you want to affect the hydronium hydroxide balance in your solution, just move the pH over, then you would use the strong acid because you don't need to use a lot of it. And while you have made a very acidic solution with a pH of 1, the solution that you made with nitric acid is safer because the only risk is the hydroniums that have been created. In the case of the HF, there's a bunch of unreacted HF molecules that have not created hydroniums. But if those molecules were to say, if you were to spill it on your skin, drink it, God forbid, or something like that, all of a sudden you now have a 10 molar concentration of this weak acid, which is going to be pretty good at reacting with any potential weak bases in your body, which you have plenty of. And so that's why we don't use those. It's just an extra, you're using a ton of molecules to cause the same shift that you can accomplish with with a small amount of strong acid or strong base. So we don't use weak acids to do this sort of like, I just want to move the pH, or I want to drive a chemical reaction, something like the pharmaceutical example. You just use strong acids because it's just more efficient. Now, we're going to spend a lot of time talking about weak acids, and there's a lot of rich things that they can do and a lot of unique things that only weak acids and weak bases can do. But what we don't use them for in the lab is just, I want to lower the pH, because they actually end up being more unsafe because of how much you have to use.
All right. First video down, looking for questions on participation 227. It's going to be due Friday. Then we've got the week 7 homework due Saturday and the post lab for determining KC due Sunday. March, it's March, or will be March, if you can believe it. If you have any questions about anything, let me know. Otherwise, I'll see you in the next video.